Hey guys, Mrs. O'Donnell here. Today we are talking about probability of an event. Um, our goals are to find sample spaces, find theoretical probabilities, and use two-way tables to find the probability of an event. Make sure you guys follow me on my YouTube channel so you get the most up-to-date videos. Yeah. Go ahead and take a minute. You can pause the video and just read through some quotes that I found that just really stuck out to me today. Specifically, that 90% of the world's data has been created in the last 2 years. I thought that was so powerful, so impactful. It just shows what a growing field data science is and how important it is for everyone to know how to gather, organize, and interpret data. All right, so now I want to talk to you guys about experimental versus theoretical probabilities. So these are the two types of probability. Theoretical probability is what we expect to happen, sort of under perfect circumstances. Experimental probability is what would actually happen when we sort of try it out. For both types of probability, we have to think about all of the possible outcomes which create the sample space of an event. Okay, so for example, an event would be like flipping a coin. Okay, so in theory, if I flip a coin, I have a 50-50 chance of it landing on heads or tails, right? I have two sides to the coin. So I have a 1 out of 2 chance that it will land on heads, or a 1 out of 2 chance that it will land on tails. That's theoretical probability. Experimental probability would be if I actually went, got a coin, flipped it, and recorded, landed on heads, flipped it again, recorded, landed on heads. That doesn't just mean because I flipped it twice and it's landed on heads twice, that doesn't mean that I now have a 100% chance of landing on heads, that I'm 2 out of 2. It just means that I need a bigger sample space to be able to better see what my probability is doing. So for example, I would have to keep flipping. So I'd have to make my experiment bigger and bigger and bigger to see what's actually happening with the coin that I'm flipping. Okay, so speaking of flipping a coin, let's take a look. If we consider flipping this coin, which has a heads and a tails, and we also consider rolling a regular 6-sided dice. So a 6-sided dice has 6 sides, all equal likely that we'll land on 1, 2, 3, 4, 5, 6. And we want to list out all of the possible outcomes. We're going to do that by making what we call a tree diagram. So I'm going to start with, if I flip my coin, I'm either going to get a heads, or I'm going to flip my coin and get a tails. Okay, and then after I flip my coin, then I can pick up my dice and I can roll that. And theoretically, if I roll my dice, I'll either get a 1, a 2, a 3, a 4, a 5, or a 6. And same thing if I flip my coin, or if I roll my dice, again, after I've flipped my coin and gotten a tails, I would either get a 1, a 2, a 3, a 4, a 5, or a 6. Okay, so in order for this to be a tree diagram, we have to connect it using little trunks. I have a bamboo pen, which makes it easier to write than using my mouse pad, but still not so easy. All right, so we still don't quite have our sample space, right? We know what all of our possible outcomes are, but we really want to list them out so we can see what a true sample space looks like. All right, and I'm going to go ahead and do that in, let's see here, let's change over to blue. So, all right, there we go. All right, so if I start listing out the outcomes in my sample space, I have a heads and the number 1. I have a heads and the number 2. I have a heads and the number 3. I have a heads and the number 4, a heads and the number 5, and a heads and the number 6. I also have a tails with the number 1, a tails with the number 2, a tails with the number 3, a tails with the number 4, a tails with the number 5, and a tails with the number 6. Those are all of the situations that I could possibly have if I flip a coin and roll a dice. Okay, so that means that leaves me with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possible outcomes for this event. All right. Just like at school, right? I have to take the time to erase. Okay, so that was our sample space. Can you hear me scratching my hand? All right, there we go. Okay, so theoretical probability. So theoretical probability, the probability of an event is the measure of the likelihood or chance that the event will occur. Probability is always a number between 0 and 1, and it can be expressed as a decimal, a fraction, or a percent. So most of the time when we're calculating probabilities, we use fractions because they're the easiest way to sort of represent the probability. And then depending on what we're doing with the probability, oftentimes we turn it into a decimal or a percent. So if we need to use that probability in some other way, we'll typically use the decimal equivalent in some type of formula. But if we're talking about our probability, right? So like, I want to know what's the probability it's going to rain tomorrow, then we typically would say the percent, right? So there's a 30% chance it's going to rain tomorrow. I don't know if that's true or not, but you guys get the point. So the way we write our probability, we use sort of function notation, this P of A, and the way we calculate it is we take the number of ways that the event can happen, all right? So the number of ways that we have sort of a successful event in our sample space of whatever it is we're looking at, we're looking for, divided by the total number of outcomes. So the total number of outcomes in our sample space. Okay, so let's look at an actual problem so we kind of have some context to this, right? So we just went through all of that work of coming up with this sample space for flipping a coin and then rolling a dice. Sorry, my bamboo pad's acting up a little bit. So flipping a coin and rolling a dice. We came up with our 12 different possible outcomes, right? So now I want to know, what is the probability that the roll will result in an even number and the flip will result in a heads? Okay, so that means that both of these things have to happen. I have to have both an even number and a heads. Well, since I have my entire sample space listed out, I can just count them up, right? So my even numbers and my heads. So I go to my heads, which is this nice top row. I see I've got, this is an even number, 1 right there, heads with an even number, and heads with an even number. So I have 3 rolls, flips that were even. I'm flipping that around. Flips that were heads with rolls that were even, and that's out of my 12 total outcomes for my sample space. And of course, we know 3/12, that reduces to 1/4. And we know 1/4, we could say our probability is 1/4, or we could say the decimal equivalent, which is 0.25, or we could also say we've got a 25% chance of flipping a heads and rolling an even number. Okay, so now let's look at another scenario. All right. Okay, cool. So for this next scenario, this next example, it says find the probability of flipping a tails or, it's a key word here, or rolling an odd number, right? So that means that we have to think about either situation. So we can either flip tails or we could roll an odd number. So the first thing I want to do is look at all the situations where I'm flipping a tails, right? So I've got a tails right here, 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 and here, right? Now the next thing that I want to look at is I want to look for all of the situations where, and let's see here, I'm going to change my color. I'm going to pop over to, how about let's do magenta. Okay, so now I want to look at all of the situations, all of the outcomes where I have rolled an odd number, right? So it looks like my odd numbers, I've got an odd number here, 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 and here. And what you see, right? So I've got a 6 out of 12 probability of flipping a tails, and I've also got a 6 out of 12 probability of rolling an odd number. Okay, but there's this interesting thing happening that you might see. Oh no, my bamboo pad, don't go out on me. There's this interesting thing happening that hopefully you see right here, where tails, if we flip a tails and roll the number 1, we flip a tails and roll the number 3, we flip a tails and roll the number 5, we would essentially be double counting if I have a 12 out of 12 probability of flipping a heads or flipping a tails and rolling an odd number. And we can see that it's not a perfect probability of that happening. There's a heads with a 2, a heads with a 4, and a heads with a 6. And those are all outcomes that we wouldn't be getting under this circumstance. So we want to be careful not to double count. Okay, so for doing this, we're still going to find the total number of ways it can happen divided by the total number of outcomes. Our total number of outcomes has not changed. We still have 12 total outcomes, but we're just not going to double count, right? So we're just going to count each underlined outcome once. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So I've got my 9 out of 12 would be that probability. I know 9/12 reduces down to 3/4, which I could also represent as the decimal equivalent of 0.75, or I could also represent it as 75%. Okay, any one of those. Okay, so you just want to be very careful with your wording, right? And or are two different types of probability. Okay. All right. I have to get my eraser. Okay, so now we're going to talk about two-way tables. So two-way table is a frequency table that displays data collected from one source that belongs to two different categories. Okay, so again, it's just a way of organizing your data. So what you can see here, they're showing you your categories, and then they're really breaking it down. It looks like they did a survey of freshmen and sophomores concerning mobile access. So 55 freshmen have mobile access, 22 do not. Right, so we know that they have interviewed, okay, so we could come down here and kind of extend the table. They've interviewed 77 total freshmen, right? We do the same thing with the sophomores, okay? We know 63 of the sophomores that they interviewed have mobile access and 12 do not, right? So we can extend the table and see that they interviewed 75 total sophomores. Okay, so to figure out the total number of students surveyed, you would just add up those totals. Okay, you could also add up the totals of students that do have mobile access, the total of students that do not have mobile access, and you can use those numbers to help you find different types of probability. So maybe, for example, you want to know what is the probability that a freshman or sophomore is not going to have mobile access. Well, that would be 34 out of 152. And it looks like that's about all the time